line that I haven't yet to look at. But to really flesh out all the details here, there is quite a lot. I'm just trying to do enough so that you have a sense of how we calculate with the wedge product, right? And in short, the way we calculate with the wedge product is just like usual. We distribute, we get addition, we get subtraction like we do with the product usually. The only rub is we have to be careful when we switch the order of things, we get a minus. So it's a lot like the cross product. And yet it's not the cross product because the cross product of two vectors is what? It's a vector again. The wedge product of two vectors is a two vector. It's something new. Okay, so that's, in short, the algebra in, that's about all I want to say about the algebra in n dimensions. But the next thing I want to tell you is, in addition to just doing algebra, we can do calculus on differential forms. So, so let me show you how we do calculus on. By the way, you can prove the product of the determinants rule in about a half a page with this notation. Do you remember proving the product of determinants rule in linear algebra? Did he do it? If you knew, I mean, if you know what's good for you, you don't prove that. It's a pain. It's like the the determinant of the product is the product of the determinants.
Yeah.
And that was 2 weeks of your course, was it not? Because you had to go down into elementary matrices, you had to look at the invertible and the non-invertible case, and you built it up from the ground as a statement about how elementary matrices obey the product rule, and that bootstrapped your way up to the formula for the product of the determinants. That's the standard proof. I'll give you a homework problem, and I'll try to walk you through how we can prove it with wedge products. It's about a half a page. It's, yeah. Now, okay, so definition. If alpha equal to the sum over I of alpha I dxi is a p-form. A p-form is a differential form built with p differentials. So that means that the alpha sub I for a specific choice of I is a function of Rn. Then the exterior derivative d alpha is a p plus 1 form given by d alpha equal to, and get this, the sum over I of d alpha I wedge dxi. D alpha I, how is that defined? This is the sum, let's say j equals 1 to n, of partial alpha I, partial xj, dxj. This is the differential we talked about in calculus 3. That's the ordinary differential of a function. This rule collapses to ordinary differential. If you take a function, you take the differential of it, you go from a 0 form to a 1 form. The differential of a function is a 1 form. The differential of a 1 form is a 2 form. The differential of a 3 form, 4 form, and so forth. The reason it's called an exterior derivative is because it starts with one kind of object and it gives you another type, right? So this is the exterior derivative. Let me, and it has various properties, right? So here are the properties of it. Number one, the derivative, exterior derivative of alpha plus beta, guess what? It's d alpha plus d beta. 2, if you have the derivative of the wedge product, then you have what's called a graded Leibniz rule. It works out as d alpha wedge beta plus minus 1 to the something alpha wedge d beta. And the something that goes there is actually the degree of alpha. So degree of alpha, so P form, another way to say that, degree, the degree of alpha equals to P. So when I talk about the degree of a differential form, I'm talking about the number of differentials that are wedged to form it. But the exterior derivative satisfies a graded Leibniz rule. It's called graded because it's sometimes plus, it's sometimes minus. It depends on the degree of alpha. Let's see here, what else? Of course, if you have a constant, you can pull it out. But perhaps the most famous and fascinating rule for the exterior derivative is the following. If you do it once, and you do it again, it's 0. The exterior derivative of the exterior derivative is 0. So in short, you could say d squared equals to 0 in that sense. These things can all be proved essentially from the definition paired with the fact that the differentials commute, like anti-commute, the minuses, and the fact that partial derivatives are like linear and they're symmetric, like partial x, partial y is partial y, partial x. Those facts conspire together to give you these properties. But rather than prove any of those things, I think I'm going to show you more examples. I think that's probably going to be more beneficial. So let's look at an example of an explicit exterior derivative. So if alpha is equal to xy dz plus w squared dx, then this would be, I'm in R4 again, right? What's d alpha going to be equal to? Right, the derivative of the components, so it's dxy wedge dz plus d of w squared wedge dx. Now you already know how to take the differential of functions. That's calculus 3, right? It might be one of your happy places, I don't know. So, all right. dxy is what? It's y dx plus x dy, all wedge dz. And this guy is 2w dw wedge dx. So what do we got here? We've got y dx wedge dz plus x dy wedge dz plus 2w dw wedge dx. There you go. The exterior derivative of this one form is a 2 form. Now, hey, if I'm right about this item 4 property, what would happen if we exterior differentiate this again? It should be a 3 form. That's true, but what else should it be? I claim it's 0. Right. It does? Oh. Yeah, I don't know yet. I mean, I believe you. So like the last one, when you wedge it, when you take the differential, you get 2 dw wedge dw. So that just kills itself. It's gone, right? So this one goes away because the differential is matched again, right? That's 0. dw wedge dw is 0. But these ones cancel because what? The negative. So it's the same, except that this and that has to be flippity-flopped, right? And so when you flip them, you get a minus on the first one, you get a plus on the second one. This and that cancel. We get 0. And actually, the reason that that went to 0 is exactly what's involved in the proof of the property 4. It's that like either you get differentials which kill themselves because they're repeated, or you get this cancellation between putting the differentials back into a common order. All right, so you're like, this is weird, you know? This is I've never seen this before. Like, what is the deal? Like, why are we doing this? What's the point of all of this? What does it get for us, you know? Well, so the bigger picture of differential forms is that you can study the shape of spaces using differential forms. Essentially, if a shape has a certain space in an abstract sense, it will or won't allow the construction of a differential form of a particular type over the space. So you can detect holes or the absence thereof in terms of the existence or the non-existence of certain kinds of differential forms. And what I'm describing loosely is what's called algebraic topology. These can be used to construct something called the de Rham cohomology, which we can use to detect holes or abstract holes, if you will, in a space. So that's kind of like one of the things that's attracted so much attention to this. But the larger point is it's a way for us to do calculus, to attach ideas of calculus to k-dimensional spaces. All right? Just to skip way ahead for just a second. If you have a k-form, all right, and you want to integrate a k-form, all right, suppose this is a k-form. If you had a space, which is itself a k-dimensional space, you can integrate this form over the space essentially by just dropping the wedges and doing the ordinary integral, k-fold integration.
So you wouldn't do the wedges, or would you not even get rid of the zeros if there were?
You just, well, that I mean, if there's repeated things, then that goes away. But the ones that remain, you do integration over those k variables. That's essentially it.
So you just treat it like they're equal.
Yeah, there's no wedges when you actually do the integration. All of the anti-symmetry is captured in the coefficients. And this precise definition of how this is done in terms of like the pullback to the space. I mean, there's some fine print here. But the bottom line is there's a natural way to integrate a k-form over a k-dimensional subspace of Rn. So we can say, and then like doing that kind of integration over that space says something about the space. It gives us information about the space. So now that's kind of the big picture. But let's get back. Let's be much more explicit. All right, in the time before the break. Let's go back to 3 dimensions. All right? Let's talk about differential forms in just 3 dimensions. So this is a talk I often give at the end of Calculus 3. Because in 3 dimensions, we can be much more explicit. In 3 dimensions, what kind of differential forms do you have to work with? You have 0 forms. You have 1 forms. You have 2 forms. And you have 3 forms. Remember, even in n equals 2, we learned that there was no 3 form. That little argument I gave you in n equals 2, that we had the repeated basis thing if we get past 2, that continues to be true in higher dimensions. If you're in n dimensions, the most you can do is an n form. Because if you go past n, you have to repeat a vector. And when you repeat the vector, it wedges to 0. So the n form in n dimensions is called the top form, or the volume form, because it's as big as it gets. So 0 forms functions. 1 form, let's say alpha equals to a dx plus b dy plus c dz. Now I'm going to introduce some special notation just for this discussion, all right? Now I'm not going to work out everything here because these make really, really nice homework problems. And I don't want to steal the joy from you. This is, and I like these for homework problems much more than if I was to say burden you with that PQ thing I did. Like, you don't want that for a homework problem. It's all about the combinatorics that I don't really care that much about in here, right? But in 3 dimensions, you don't really have to deal with the combinatorics. You could just do it, brute force, right? It's a little bit of writing, but not too much. So there's a definition. We're going to say that this is the work form, omega, of the vector field ABC. So this right here is my definition of work form. The work form correspondence. That's the 1 form corresponding to the vector field ABC. Likewise, a 2 form has the form, well, A, D, and watch out here. I'm being very careful in my choice of things here. So this is going to be dy wedge dz plus b dz wedge dx plus c dx wedge dy. Now, if you're really good at your combinatorics, you'll realize that I've violated my ordering rule earlier, because earlier I had 1, 3, and now I've got 3, 1. But that's just for the purpose of making this map natural. And so this is the flux field, the flux form, sideways TIE fighter, of vector field ABC. Definition, flux form correspondence. Flux form. This guy up here, work form. I wish I could tell you the name of the author of the book I found those terms from. It's this kind of pastel green book. I can't ever remember his name. My apologies. He probably didn't invent it either. I'm not sure who did this first, but 3 form, G, dx wedge dy wedge dz. So 0 forms and 3 forms, there's just one of them. I mean, there's just the number 1 times a function. That's the only kind of 0 form there is. There's just a function times this volume form. That's the only kind of 3 form there is, right? So what do we do in Calculus 3? We study vector fields, right? We study their cross product. We study their dot product. We integrate them, all that stuff. So the first thing that I'd like you to do is prove the following, theorem. This will be one of your homework problems. Omega vector A wedge omega vector B. So here you should let A be like, A1, A2, A3, something like that, You make them, you use whatever notation you want, but you need to invent letters for A and B's components so you can work out this problem, right? Maybe when I write up the problem, I'll give you names for the components just to make sure you're on the straight and narrow, to make my grading easier. But guess what? This is the flux form of what? It's the flux form of the vector A cross B. In fact, that's what happens. If you take the the work form cross the flux form of, let's say, B, what you get is A dot B dx wedge dy wedge dz. Let me write it a different way. If you take the work form of A, wedge the work form of B, wedge the work form of C, you get the work form of A, wedge the flux form of B cross C. But that's the dot product of A with B cross C, the so-called triple product. Do you guys remember the triple product from Calculus 3? What's it tell you? The volume of what? So if we've got like B is like this, and C is like this, B cross C is a vector perpendicular to those, right? If A is like this, A dot B cross C, it gives you the length of essentially this. So if you were to take that tilted parallel pipette and just put it flat into a straight rectangular cube, the volume of it is A dot B cross C. This is the volume of the parallel pipette with sides A, B, C. And of course, the area down here is what? The magnitude of B cross C, right? That's the area parallelogram. So this is the volume of the parallel pipette with sides A, B, C. Parallel pipette, or is it parallel? I don't know what stupid thing's called. It's a... and you know, this is also equal to, going back to what I started with, the determinant of A, B, C. That is that number. That's the formula I had written at the top of the board, showing up again. It's just instead of having E1, E2, E3, I now have dx, dy, dz, but the mathematics is the same. It's the same pattern. So that's kind of neat, a little bit. You know, the wedge product is associative. So it doesn't matter if I do AB and then BC, right? Is the cross product associative? It is not. So how is it that we're getting this wedge product, which is associative, to construct a cross product, which is non-associative? How does that go? Yeah, I mean, well, partly it's not doing it directly, right? It's like, you see that as kind of a funny game. We're picking up the cross product, not at the same, like the cross product of the cross product of the vector fields encoded by one forms is giving us the two form, which corresponds to the cross product, right? It's like, it's not direct. It's, but the associativity down here, if you cycle through the different associativities, it would go back to the cyclicity of the triple product. Like you can flip this around. You can go B dot C cross A, and you can cyclically permute these. It doesn't change the answer. If we change it a different way, it puts a minus. All right, great. So that's the wedge product. Now there's one other thing we can do with in 3 dimensions that's especially, actually you can do this generally. Remember Pascal's triangle? What was there? There's a pattern, isn't there? So if you start looking at this, you can start seeing that there's always this like symmetry, isn't there? Between, say, this and that, or this and that, or this in itself, kind of stupid, but, and so remember I said this would be like n choose how many? Oh, this is, well, fine, this is, I'll just write it as n. This is n choose 0. This is n choose 1. This is n choose 2. This is n choose 3, n choose 4. Did I do this wrong? 0, 1, 2, 3, 4. N choose, am I only to 5? Oh, man. Oh, thank you. I was about to get really, really confused, so thank you. Oh, look at this. Look at this. I drank the coffee too early today. That was a mistake. I should have saved it. So there's something combinatorial that's kind of cool. N choose k is equal to what? N choose n minus k, right? For example.
Yeah, because they have the,
So, for example, in 3 dimensions, we have 3 choose 1 equals to 3 choose 3 minus 1, 2. In 3 dimensions, the number of 1 forms and the number of 2 forms is equal. And in vector space, you learned that when things have the same dimension, you can make an isomorphism between those things. There's a one-to-one bijective linear transformation that you can build by just mapping the basis to the basis, right? I mean, you may or may not have emphasized that in linear, but it's true. So there's something miraculous about 3 dimensions, that the number of 1 forms and the number of 2 forms matches up. That's why we can use vector fields to describe both the objects which are more natively described as 1 forms and the ones we can describe as 2 forms at the same time. That's a very special coincidence to 3 dimensions, right? But the isomorphism I'm talking about down there is what's called Hodge duality. So the Hodge duality in a nutshell, it's more difficult for me to describe. There's beautiful abstract linear algebra to learn here, but I'll just leave it at this. For R3, the Hodge dual of the number 1 is dx wedge dy wedge dz. The Hodge dual of the work form with vector field A is the flux form with vector field A. So Hodge duality is the duality which changes your work forms to flux forms and back forth. The Hodge dual of the flux form is the corresponding work form. So Hodge duality trades a p form for an n minus p form. It takes a 1 form to a 0 form, rather, to a 3 minus 0, 3 form. It takes a 1 form to a 3 minus 1, 2 form. It takes a 2 form to a 3 minus 2, 1 form. This is how Hodge duality works in 3 dimensions. So with Hodge duality, you could write additional formulas, all right? With Hodge duality, you could actually write a formula for the dot product using Hodge duality. Like, I could write well, anyway,